A tale of terrific pteropods. I hope you're sitting comfortably so I can tell you a tale about my favourite species of planktonic snail. They're called pteropods, spelt with a silent P, and they live at high and low latitudes out in the sea. Why do I study these snails? You'll want an explanation. Well, they're early indicators of ocean acidification. This occurs when CO2 dissolves into the ocean, changing its chemistry. It's quite a commotion. Carbon dioxide and water make H2CO3, known as carbonic acid to you and to me. This acid splits into ions of bicarbonate and hydrogen, lowering the pH of the ocean. The ions of carbonate decrease as well, and these are the building blocks of a pteropod shell. With fewer building blocks, it will take more energy to build a carbonate shell from the sea. But why are they important? If they disappear, will we know? They are, after all, the size of a flake of snow. They live in the surface ocean, but when they meet their fate, their shells fall to the seafloor, shuttling carbonate. And let's think about the food chain. What eats a pteropod? They're snacks for seabirds, krill, and juvenile cod. So if pteropods decline and you enjoy eating chips and fish, you might find there's a price increase of your favorite dish. I've focused my work on the shells of pteropods to learn about the resilience of these little gastropods. I look in the microscope and image every shell, then some lucky specimens get CT scanned as well. CT scans combine X-rays from many orientations to create three-dimensional representations. This 3D data can be used to quantify shell thickness and volume of each sea butterfly. We use this method to see how pteropods fared. If their shells start to dissolve, could they be repaired? The samples came from the Greenland Sea, which experiences ocean acidification seasonally. There were signs of dissolution on more than one shell, white marks on the surface from when pH fell. CT scanning showed that these patches on the surface were both thicker and thinner depending on their place. Where shell repair had happened, we could now tell the repaired part was 3 times as thick as the original shell. For us, this finding was absolutely brilliant, as this repair mechanism makes pteropods more resilient. With that said, there's still a lot we don't know about energy requirements to fix the shell from below. Will this affect the development of the swimming snail? Will reproduction be delayed? Will the shell be more likely to fail? So let's take a step back and think about the cause of this problem. Why are the oceans becoming less hospitable for them? Remember, ocean acidification is caused by increased CO2. It's at the source of this problem that we have work to do. Carbon dioxide emissions come from burning fossil fuels, which we use for transport, heating, and industrial tools. So we need to reduce our CO2 output to make sure pteropod shells don't go kaput. Let's move to green sources of energy, cycle to work, insulate homes, and harness energy from the sea. Eat less meat and more plants, a lower carbon diet. And if green issues come up in politics, we mustn't keep quiet. The impacts of high CO2 are wide-ranging, affecting animals and humans worldwide. Something needs changing. So let's work together and create a better world for you and me, but also for our favourite plankton pals out in the sea.